This video provides an introduction to dynamic operations in CHEMCAD. We'll talk about the difference between dynamic and steady state modes in CHEMCAD. We'll introduce the ramp function, which is a way of driving dynamic behavior. We'll also do a brief introduction to some of the properties of dynamic vessels. We'll also talk about how to report dynamic values for streams and how to get runtime plots for selected process variables. Specifically, at the end of this video, assuming you work along with me as I go through these examples, you should be able to switch CHEMCAD between steady state and dynamic modes. You should be able to set the runtime and step size for a single step dynamic process. You should be able to set up the ramp unit operation for ramp, step, sinusoidal, and random inputs. You should be able to select streams and variables to record and to display during runtime. You should be able to make plots of recorded variables and export the plot data to Excel. And you should be able to use the dynamic vessel unit operation in its constant level mode. To illustrate these, we're going to start with a very simple example where we dilute glycerin with water to make a dilute glycerin stream. So I'm going to switch out of PowerPoint and into CHEMCAD, and we'll build the flow sheet. We've got CHEMCAD running off campus through a VPN connection. I'm going to go ahead and set the font to be an Arial 36. That will make the flow sheet look more like an actual process flow diagram. We need to select our components. So our two components are water and glycerol. And let's set this so we can maybe operate at a little bit higher temperature. We won't need it for this example, but might as well just in case we want it for the future. So we've got the non-random 2 liquid model for our mixture thermodynamics. And just reviewing the thermodynamic settings quickly, there's nothing that we need to adjust here. We're not going to get liquid-liquid phase splitting because water and glycerin are miscible in all proportions. And we're at a pretty low pressure range. So we'll take OK for these. And another thing we need to do is specify our engineering units. I'm going to work this in American engineering units, which means our mass rate is going to be in pounds, temperatures in degrees Fahrenheit, pressures in PSIA, and times recorded for streams are going to be in hours. When we run the simulation, I'm actually going to specify minutes for time steps, but our flow rates will be recorded in something like pounds per hour. So these are all okay. So let's build the flow sheet. We're going to start with our feeds, our water and our glycerin. We need to mix them, so we'll add a mixer unit operation. Remember, the mixer in this case is probably nothing more elaborate than a T. And then we'll take a product from these two. And let's connect them up. And make sure our flow sheet is tidy. And first thing, we'll set let's make this stream 1 to be our glycerin stream. So let's edit that. Let's say it's coming in pretty warm to drop the viscosity. Let's bring it in at 50 psig or 65 psia. And we'll start with 1,000 pounds an hour of glycerin in this stream. And for this other stream, we'll take water. And let's say that's coming in at 100 degrees Fahrenheit. 65 psia, and we'll say 9,000 pounds an hour of water. So we can now run this very elaborate flow sheet, and you can see our final product is in fact 10% glycerin and water, just as we expected. Let me go ahead and label this. It's always good to label your key streams. Okay, we now have our steady state flow sheet. What we need to do is put the flow sheet now in what we call dynamic mode. So far, everything you've seen with CHEMCAD has been in steady state mode. To switch to the dynamic mode, we can use the run menu. You can see that we have an option here to switch between steady state and dynamics. You default in the steady state mode, and you're used to all these options that you've got here. Probably mostly you've used the run all option. Now we're going to switch it into the dynamic mode. And you can see now that I've done that in the run menu, the run steady state options are grayed out, and I have all these run dynamics options. So the first thing we need to do is set the runtime. CHEMCAD has the option of breaking operations into multiple steps. You might think of them as stages rather than steps. For instance, you might heat a reactor to a certain temperature, then add a reactant, heat it to another temperature, something like that. In this case, just to illustrate the dynamic capabilities of CHEMCAD, we're going to use a single step in the operation. We're going to let that step run for 300 minutes, and we're going to have CHEMCAD report out process results at 1 minute intervals. That's what this step size is about. At this point, CHEMCAD doesn't do anything dynamic because we haven't told it to do anything other than take these two constant flow feed streams. So what we're going to do is add this ramp function. I like to place the ramp function close to the stream or unit operation that it's manipulating. When we go into the ramp function, you can see that you can vary a parameter either for equipment or for a stream. So in this case, what we're going to do is vary the flow of stream 1. And the variable we're going to vary is the total mass rate. And let's say, that's just to confirm this. Now, before I fill the rest of this out, we need to talk about what this ramp function is going to do. Right? As I mentioned, the ramp function is a tool to drive a dynamic input. We can change one variable at a time with each ramp unit up. If you need to change more than one variable, you can add more than one ramp. So you might have remembered when I just showed you that operation, you could see a table. In the table, CHEMCAD will just do a linear ramp from each entry in the table to the next one. You can specify random values, meaning CHEMCAD will just put random numbers in at each time step, or you can specify a sine wave input by giving a baseline, an amplitude, a period, and an offset. We'll go through examples of each of these. So what we're going to do is record the glycerol stream and the product stream. The water stream is not very interesting because we're not going to do anything to it. During the simulation, we'll watch the glycerol flow rate and we'll watch the product composition. We'll simulate this over a 3-hour period at 1 minute time steps. And as I mentioned, we'll go through the ramps, the step changes, the sine, and the random operations. So the first thing we'll do is ramps. We'll start the glycerin rate at 1,000 pounds an hour. We'll run for 30 minutes, then we'll ramp it down from 1,000 to 500 pounds an hour over a period of 1 hour. We'll ramp it up to 1,500 pounds an hour over a 30-minute period, then ramp it down to 1,000 pounds an hour over 2 hours, 120 minutes, and we'll hold it there for the final final hour of the simulation, going to 360 minutes. So this is what that ramp will look like. You can see we start at the 1,000. After 30 minutes, we ramp it down to 500, then we ramp it up to 1,500, back down to 1,000, and then let it run out at 1,000. We'll now flip back to CHEMCAD and take a look at how to set this up. Okay, you might remember this screen. We're going to use the table here to set up the ramp. So we're initially at 1,000 pounds an hour of the total flow of stream 1. After 30 minutes, we're still going to be at 1,000 pounds an hour. Then at 90 minutes, we're going to ramp it down to 500 pounds an hour. At 120 minutes, we should be back up to 1,500 pounds an hour. Ramp it back down to 1,000 pounds an hour at 240 minutes, and then let it run out at 1,000 pounds an hour. So I've got my ramp set up. Now we need to take a look at how to record streams. If we go to the Run menu to Dynamics, you can see this Record Streams option, and you get this nice table. So what we want to record stream 1, and we want to record stream 3. And you might remember that we said we wanted to get runtime plots for each of these so we could see what was going on during the simulation. Once we've selected these, we can say OK. For stream 1, we don't necessarily want to look at it in the compositions. We do want to see the stream properties. And the interesting stream property is going to be the mass flow rate, because that's the only thing that really changes. So we'll say OK to that. For stream 3, what we'd actually like to see is the mass fraction for glycerol. So we'll say OK to that. And we now have all of our run parameters set. So you can see I've got these dynamic run options here. This is to set up the runtime. We did that already, going from up to, meant to go to 360 minutes. Glad I caught that. 360 minutes. This resets us to the initial state. Okay, the system is currently in its initial state, so we don't need to do it. Anytime you make a modification to the flow sheet, you need to be in the initial state. Now we can run the simulation. And you can see I'm getting these runtime plots that, not surprisingly, parallel each other. But you can see this is the chart for the mass fraction of glycerol in the product. This is the glycerol flow rate here. So they should be exactly parallel to each other. And you can see also that CHEMCAD does some automatic scaling as we go through the process. They're very, very good for diagnosing what's going on and to get a feel for what's happening dynamically in your process. But if you want to see all the details, the easiest thing to do is to take the stream you've recorded and go to this Plot Dynamic Streams option. And here, I'd like to plot the stream property, mass flow rate. It remembers what I've recorded here. And now you can see the mass flow rate of the glycerol stream over the entire simulation. I can do the same thing for the glycerol concentration in this product stream. Right, stream 3, glycerol concentration, and we start at 10%, we end up at 10%. So this all looks like we would expect it to look. The next option we want to look at in the ramp function is making step changes. The ramp function doesn't have a way of doing that explicitly, so what you can do is run the previous process condition up to the time step before you want to make the step change. So you can see here, if I want to step down to 500 pounds an hour at 30 minutes, I'll use the ramp to say go from 1,000 at time 0 to 1,000 at 29 minutes. Then at 30 minutes, drop it to 300. And if you look at the slide carefully, you can see how I've set up all these step changes to work. What we're going to expect to see are these step changes. And you can see that it's not really obvious that these aren't sharp changes, that these are there's actually a minute over which these changes occur. So let's make these changes in the ramp function. Before I change anything in the ramp function, I need to return to the initial state. Otherwise, the changes I make won't stick. And we get this little warning, I'll continue to take them here. Say continue. Then let's edit our unit op data. We're still really using a ramp. I'm going to go to 29 minutes. Then at 30 minutes, we drop to 500. At 89 minutes, we're still at 500. And then at 90 minutes, we pop up to 1500. And then at 119 minutes, we're still at 1500. And then at 120 minutes, we're at 1000. And at 360 minutes, we're still at. So let's run this. And you can see we're getting exactly the step changes we expected to see. Let's take a look at our full simulation here. Let's actually plot the streams. And you can see, again, we have our drop at 30 minutes, our bump up at 90 minutes, and our drop back down at 120 minutes. If we look at our product and plot the mass fraction glycerol, again, we get the same very nice parallel data. A nice shortcut for you if you start to feel you're getting pretty cluttered with charts. If you go to your window option and click close all charts, it will close all of those for you at once. The next option we have for the ramp function is a sine function. So that has basically going to set a baseline for the sine, an amplitude around which that varies, a period for the variation, and an offset, meaning how long are you delayed from your time 0. So if this offset had been 0, we would have started 0 and hit it up at time 0. So this is the function that we're going to be simulating in CHEMCAD. So remember, the first step in dynamic mode when we want to change anything is to reset to the initial state. And let's now edit this unit operation. And still modifying stream 1, but now rather than using a table of data, we're going to put a sine wave input. My baseline is 1,000. My amplitude is 500. I'm going between 50 and 1,500 pounds an hour. My period is 60 minutes, and we're going to offset the time by 30 minutes. So that's simple. Let's run the simulation. And again, we get the results we expect to see. The final ramp mode is this random mode, where you give it an upper and a lower bound, and you tell CHEMCAD to pick random values at each time step for this variable. So they're uniformly distributed, not normally distributed for those of you who are interested in statistics. Let's see how this plays out in CHEMCAD. Again, reinitialize. Edit the unit op data. And now we want to take a random disturbance. So we're going to go between 500 and 1,500. And let's run it. And let's run it. Okay. And you can see we've got our random input here and our random output here, and exactly the behavior we expect to see. Let's clean up some of these windows. Now we have our workspace in CHEMCAD cleaned up. Let's pop back to PowerPoint and talk about dynamic tanks for a moment. Okay, in a dynamic tank, it will assume that you have a perfectly stirred tank. You need to provide the diameter, the height, and the type of tank head you've got. You need to specify initial conditions, meaning a level and initial charge. And this unit operation actually has several operating modes. For now, we'll work with a fixed level in the tank. In CHEMCAD, I'm going to pick this unit operation. The other vertical version there has a spot for a relief valve. I don't necessarily want to look at that now. So I could either have taken my two inlet streams together and fed them into this tank separately. But what I'm actually going to do is just reroute the mixed stream into the tank, just to save a little bit of screen time here. I recommend that you have at least 2 exits from any tank dynamic vessel you set up. One of them will, like in this case, will be the liquid product. The other will be a vent. You need that just to make the unit operation work right. So this is our new flow sheet. So we need to set specifications for this dynamic vessel. So we're going to specify it as a vertical vessel. We're going to give it a diameter of 4 feet, a height of 12 feet. You have the option to say a little bit more about the tank geometry, whether it's got an ellipsoidal head, a hemispherical head, bumped head on the bottom, or a flat bottom. We're going to assume an ellipsoidal head. We'll take the default head ratio, which is just how much of the tank volume is taken up by heads. The tank volume you would calculate based on the cylinder height and the diameter is actually less than the total volume of the tank, because there's some liquid that will live in the dish below the bottom of the straight side of the tank. We're going to run this tank adiabatically at the inlet pressure of 65 psi. We're going to take as our initial condition the outlet stream composition, and we'll give it an initial liquid level of 8 feet. That's just a number I pulled out. You might be wondering how we have an outlet stream composition. We'll need to run a steady state simulation first to get that. For the outlet flow, we need to specify constant level. Okay, and that puts us in this mode. And we can specify now a liquid level. I'm going to specify 8 feet. And that actually gives us everything we need to run this vessel. So let's switch our input back to one of these tables. And here's our set of step changes. CHEMCAD has very thoughtfully remembered those for us. So let's just run those. And before we do this, let's put this into steady state mode, run it once, and now you can see that this liquid composition is now set. Now we'll put it back into dynamic mode. Before we run this revised simulation, we need to also make sure that we track the composition of this outlet stream from the tank itself. So let's select this stream, or go back to our run menu, say run dynamics, record stream 4, and let's look at its composition during runtime. CHEMCAD will actually step through all the streams you're recording when you do this. So stream 4, let's look at mass fractions, and let's look at the glycerol concentration in that stream. And now we're ready to run. Okay, so you could probably see in this outlet liquid stream 4 composition graph that we were getting some of the first order behavior you'd expect from a tank. So let's look at that stream with the runtime plot, or with the dynamic stream plot rather. And you can see here's our first step change, our second step change. We hadn't really even made it all the way through that step change when we got to our third step. All right, so let's actually slow down our input to this process a little bit. But before we do that, reset back to initial conditions. And let's say that at 30 minutes, we move it from 1,000 to 1,500. And let's get rid of the rest of these. Now let's run that with just a single step change. And of course, now we've run it for a ridiculously long amount of simulation time. But let's take a look at the dynamic stream plot. And you can see we get this very classic first order behavior. Remember, the 30-minute time offset is something that we specified as the timing for when our set point where a disturbance change occurred. Now let's switch from using a step change input to a sinusoidal input. So let's bring it back to initial time. We'll edit the unit op data, sine wave. You have to be careful with these because CHEMCAD doesn't always remember things quite the way you would expect them to. Baseline, remember, should be 1,000, and the amplitude should be 500. Period still 60, offset still 30, so those are good. So let's run these. And you can see here that I made a mistake previously. Let's take a look at a random input also. Reset this. Take the random disturbance, going from a minimum of 500 to a maximum of 1500. 1500. And let's run. Okay, and you can see from this dynamic stream plot, let's take a look here. Plot for stream 4. And you can see that there's a lot less variation locally. That's because the process itself is damping out a lot of the random variation. If we were to run this again, we'd actually get a different result, because this input is in fact random. So here's the previous version, here's the current version. One last thing to look at. Let's take a look again at our step change behavior. And let's edit this to go back to our table input. So you can see our step change is still here. So let's run this one more time. And what might be useful would be to have this data available to you in something like Excel. So if you go into the dynamic plot view of this, for this data, and go to your chart menu, you can see that you can take your data into an Excel CSV file or into a semicolon delimited file. So if I do this, then I now get a table of mass fraction versus time. And I can now make plots or run statistics or estimate time constants or whatever I want to do with this. So it's important that you know that you have that option, so that if you're trying to, for instance, tune a controller based on a process response curve, you have a way of getting that process response data other than just trying to read it off a chart. So to summarize where we've been, you should now be able to switch CHEMCAD between its steady state and its dynamic modes. You should be able to set runtime and step size for a single step process. You should be able to set up a ramp for actual ramp inputs, step inputs, sine inputs, or random inputs. You should be able to choose which streams and variables you want to record and display during the actual CHEMCAD run. And you should be able to make plots of the recorded data and export that plot data out of CHEMCAD. And you should also at this point be able to at least use the constant level mode of the dynamic vessel. We'll talk about some of the other options for the dynamic vessel unit operation in a future video. Hope this helps. Let me know if you have questions.